Okay, so in this video, we will figure out whether the following series converges or diverges. So again, let us look first at the series from an intuitive perspective. So, as we are summing the terms of the following sequence as n goes from 1 to infinity, we ask quite simply, what are the driving forces of our sequence? So what is the dominant term on top? Well, on top there is a single term, n squared, over on the bottom that the dominant term is n cubed. So we're summing complicated terms, but these terms, as n gets larger and larger, will be approximately yielding the fraction n squared over n cubed. As again, n squared is the dominant term on the numerator, as n cubed is the dominant term on the denominator. If we simplify now this new series, we have simply 1 over n. This is a traditional p-series where p is 1, or also called the harmonic series, and we know that for a p-series where p is 1 or smaller than 1, the series diverges to infinity. So now we have the intuition. This complex-looking series is roughly the same size as a divergent p-series, which blows up to positive infinity, so intuitively, we expect this series to blow up to infinity as well. Now we have to prove that our intuition is correct, and to do so we will apply the limit comparison test. So we can call the initial sequence an, and the simplified new sequence bn, but what's interesting is when we look at the ratio, because what we have to show, if you remember the limit comparison test, is that the ratio of the original sequence an over the new sequence bn will be approaching a positive number. If that is the case, then our intuition is indeed correct. In this case, both series, the original and the new one, will diverge to infinity. What's interesting is we are better off taking the unsimplified version of the new sequence, and you will see why in a second. So again, all that remains now is to prove that our intuition is correct. Basically, that this inequality is rigorous by showing that the ratio of an over bn will be approaching a positive number. So let's rewrite an. If we divide by a fraction, we then multiply by its inverse. And now what I will do is pair up the dominant terms. You can see this term is divided by n squared. So I will bring this over n squared as a 1 over n squared on the numerator. Let me rewrite the initial denominator on the left. And you can see here this n cubed multiplies the numerator, but if you bring it down as its reciprocal, if you divide twice, you get the same thing. Right? 1 over n cubed is times n cubed. And you can see now that by keeping the unsimplified form of the new sequence bn, by keeping the dominant term on the numerator, the dominant term on the denominator, and not simplifying them, when you then divide an by bn, the dominant terms will cancel the respective origin. So this was the dominant term on top, it will cancel the dominant term on top. This was the dominant term on the bottom, it will cancel the dominant term on the bottom. So now let's multiply through. On top we have something trivial, 1. On the bottom we get here 1, n cubed over n cubed, plus n over n cubed, 1 over n squared, plus 1 over n cubed. And now the result is trivial. 1 over n squared, 1 over n cubed, both converge to 0 as n tends to infinity. So the ratio of an over bn as n tends to infinity will be approaching 1. So this proves that our intuitive argument is correct. If in the limit an over bn approaches 1, then this implies, of course, that as n tends to infinity, an over bn since it is getting closer and closer to 1, will be approximately 1. So that if we multiply by bn, then an will be approximately bn. And so if the terms of the sequence an are approximately the terms of the sequence bn, so will their respective summations, their respective series. And so the series from 1 to infinity of an will be roughly the same size as the series from 1 to infinity of bn. So this step is simply to confirm that our intuition is indeed correct. And again, because the simplified new series, the p-series where p equals 1 diverges to infinity, so will the original series. So let us now write down our conclusion. This implies that the original series, summing from 1 to infinity n squared over n cubed plus n plus 1, diverges to infinity by, of course, here, the limit comparison test, which I will write as LCT. And again, when you write that the series is infinite, this of course means that it converges, so you can write here hence the series diverges, which again is obvious from stating that it is equal to infinity. And that's it.